All right, we're going to start with this discussion question about jumping on that trampoline. So when you're jumping on that trampoline, when you're way up at your maximum height, all of your energy is in gravitational potential energy. And as you fall, it transfers into kinetic energy. And then as you smash into that trampoline, it changes into elastic potential energy. And it bounces back and forth as you jump up and down. So how do you jump any higher? Well, how do you increase this overall mechanical energy is you have to do work in. And so when you're jumping on a trampoline, when you bend your knees and you apply force over a distance, when you're jumping back up, that force over that distance, that's work. You're adding energy in, okay? Every single time though, you are losing energy. You know, if you were just to jump on a trampoline, stay straight-legged, eventually you would stop because as it bounces back and forth, we do lose some energy. Of course, this does have a limit. You can't just continue to put energy in forever. Either you'll hit that ground on the bottom or you'll do the inevitable. You don't have enough force in your legs to keep your body through that big acceleration here and you'll just kind of collapse onto your bottom. So let's move on to the example. So the example says stopping distance of a car, the driver of an 1,800 kilogram car, including the passengers, traveling at 23 meters per second, slams on the brakes, locking the wheels on dry pavement. The coefficient of kinetic friction between the rubber and the dry concrete is typically 0.7. Use the work energy principle to calculate how far the car will travel before stopping. How far would the car have traveled if it's going twice as fast? And what happened to all of the car's original energy? All right, so they want us to use the work energy principle, work kinetic energy theorem. So I see that it starts at one point, ends at another point. So I have to write out that work kinetic energy theorem and start crossing things off. So I think about the height at the start and at the end. Well, the height is the same at the start and at the end, so I'm going to call that height 0. I've identified point 1 and point 2, so now I get to walk through and cross stuff out. So is there anyone pushing on the car? No, no one is pushing on the car, so there's no work in. Is there friction? Yes, there is a force of friction. If I was to draw my free body diagram here, I would see I have gravity, normal force, and friction. And note, yes, it is moving forward. There is a velocity going forward, but no one's pushing it forward. Okay, and so that is not a force, that is a velocity, so it doesn't go on that free body diagram. There is friction. It is moving over a distance and they are parallel. So yes, work done by friction. The car comes to a stop at the end. It's moving at the start. The heights are the same at the start and end. And it's not like hitting a big spring or any rubber bands. So no elastic potential energy. So that leaves us with work done by friction equals negative K1. This is where we get to start substituting. So work done by friction is going to be negative force of friction because it's pointing to the left times that, times that displacement is equal to negative 1/2 mv squared. Force of friction, this is kinetic, so I'm going to substitute. So I'm substituting in mu sub k times the normal force times the displacement equals negative 1/2 mv squared. This displacement, make sure it's on there every step. That one falls off from time to time. Normal force, I'm going to have to go ahead and solve for that in my y direction over here. So the sum of the force in the y direction is 0. It is not accelerating in the y direction. Normal force minus mg equals 0. Normal force equals mg. So I can make that substitution. So negative mu sub k mg times s equals negative 1/2 mv squared. Looks like we have some things we can cross off. I have a mass on each side, so it doesn't even matter the mass of the car or the passengers included. And I have a negative sign on both sides I can get rid of. So when I'm trying to find the distance it takes to stop, I'm trying to find that s value. So here I have s is equal to v squared. I'm going to move that 2 into my denominator, divide the mu k, the g, over, so I have mu sub k times g. This tells me the distance it takes to stop. So I can plug in my numbers. So 23 squared divided by 2 times 0.7 times 9.8 will give me a distance to stop of 38.6 meters. All right. Part B wants to know, but what if you were going faster? how would that change your displacement? So let's think about that. So my relationship here is that S is equal to V squared divided by 2 mu sub k times g. So the only way to change S is if I change the coefficient of friction, meaning the road's like icy or wet, or I change my speed. And if I go ahead and double that speed, essentially I've multiplied this side of the equation by 2 squared. So that means it's going to take 4 times as long for you to stop if you're going twice as fast. This brings up an idea. When you're driving through those school zones, they drop that speed to 15 miles per hour. What is the idea there? Well, if I can say, people usually drive through a school zone maybe 30 miles an hour, and I drop it to 15, half the speed, that car is going to stop in 1/4 the distance. Not to mention how far it's going to travel in the time it takes that person to hit the brakes. So it's just giving a lot more time. It's giving a lot shorter distance for it to stop. So last part there. C says, what happened to all the original kinetic energy? So as that car skids to a halt, if you're not even watching, you can hear. There's sound, there's heat, and probably a little bit of deformation as that tire kind of breaks down as it's crushed across that concrete.